Good day, everyone. As representatives from the Department of Statistics at CUHK, we are thrilled to present to you on the fascinating topic of the chain rule and implicit differentiation. Let's dive right in. To begin, let's first understand why the chain rule is so important. While we have a set of rules that allow us to differentiate basic functions, we often encounter more complex functions that are formed by the composition of basic functions. For example, how would we differentiate the square root of x squared plus 1? This is where the chain rule comes in handy, as it enables us to differentiate composite functions. It is perhaps the most important differentiation rule of all. The way you should think of the rule is to work from the outside in. Now let's move on to the chain rule itself. Let f composed with g of x equal f of g of x be the function defined from f and g by composition. Assume that g is differentiable at the point x and that f is differentiable at the point g of x, then the composite function f composed with g is differentiable at the point x, such that f composed with g prime of x equals f prime of g of x times g prime of x. Leibniz notation gives us a useful alternative way to write the chain rule. We define u equals g of x and y equals f of u, then the chain rule takes the form dy over dx equals f prime of u times du over dx equals dy over du evaluated at u equals g of x times du over dx, or simply dy over dx equals dy over du times du over dx. Let's take a closer look at the chain rule. The chain rule can be expressed as f of g of x prime equals f prime of g of x times g prime of x. Let's see how this works through a proof. Substituting u equals g of x, and u plus delta u equals g of x plus h, so that delta u equals g of x plus h minus g of x, we get f prime of u times g prime of x equals f prime of g of x times g prime of x. Now let's interpret the chain rule using Leibniz notation. Dy over dx equals dy over du times du over dx. We interpret dy over du as measuring how much faster y changes than u, and du over dx as measuring how much faster u changes than x. Thus it seems perfectly natural that dy over dx should be the product of these two derivatives, measuring how much faster y changes than x. Think of a magnifying glass. Each object is magnified in size by a fixed amount. The chain rule then expresses the idea that if you magnify twice in succession, two lenses, one looking through the other one, the resulting magnification is the product of each separate lens. Let's see some examples to better understand the chain rule in action. Find the derivative of square root of x squared plus x for this function. Clearly, the square root is the outside function. The composition is to first take x and compute x squared plus x, then take the square root. So, since the chain rule tells you to work from the outside in, first differentiate the square root. Let u equal x squared plus x, then the derivative of square root u is d over du. Square root u equals 1 over 2 square root u, so square root x squared plus x prime equals 1 over 2 square root x squared plus x times 2x plus 1. Another example, if f x equals x cubed plus 4 times x squared minus 3 times x plus 1, raised to 4, find f prime x. The fourth power is the outside function, so it is the first thing you differentiate. F prime x equals 4 times x cubed plus 4 times x squared minus 3 times x plus 1, raised to 3 times x cubed plus 4 times x squared minus 3 times x plus 1, prime, which equals 4 times x cubed plus 4 times x squared minus 3 times x plus 1, raised to 3 times x squared plus 8 times x minus 3. One more example, differentiate y equals x squared plus 2, raised to 10, writing y equals x squared plus 2, raised to 10 as y equals u raised to 10, where u equals x squared plus 2. We have dy over dx equals dy over du times du over dx, which equals 10 times u raised to 9 times 2 times x, which equals 20 times x raised to 2 plus 2, raised to 9. As with nearly any rule, after gaining some facility with its use, one can find shortcuts. Instead of explicitly substituting u equals g of x, one simply thinks it instead. To differentiate f of g of x, Then, one thinks of the inside function g of x as an indivisible glob and recites take the derivative of f with respect to glob and then multiply by the derivative of glob with respect to x. In this way, the derivatives of many composite functions may be written down directly as one recites the rule. Let's see an example. Differentiate f x equals 1 plus 3 times square root x raised to 35. Simplification is not needed. Thinking of 1 plus 3 times square root x as the glob in this case, we immediately think and write f prime x equals 35 times glob raised to 34 times d over dx glob, which equals 35 times 1 plus 3 times square root x raised to 34 times 3 times 1 over 2 square root x. Another example, differentiate f x equals x plus 1 over x squared plus 1 raised to 3. Simplification is not needed. F prime x equals 3 times x plus 1 over x squared plus 1 raised to 2 times x squared plus 1 times 1 minus x plus 1 times 2 times x over x squared plus 1 squared. In short, the chain rule is a crucial tool that enables us to differentiate composite functions. With its help, we can differentiate more complex functions efficiently and effectively. Next, we will be discussing the concept of implicit differentiation. So, what is implicit differentiation exactly? Well, to put it simply, sometimes a function y equals f of x is defined implicitly by an equation involving x and y. Let's take the example of the unit circle x squared plus y squared equals 1, which implicitly defines the functions y equals the square root of 1 minus x squared and y equals negative square root of 1 minus x squared. However, it's often more convenient to leave the functions implicit and sometimes it's not possible to solve for y. So, how can we find the derivative dy of such implicit functions? The chain rule comes to our rescue. We differentiate both sides of the equation and apply the chain rule as needed, remembering that y is a function of x. Let's take a look at an example. In the aforementioned example of the circle x squared plus y squared equals 1, we can differentiate both sides of the equation to get 2x plus 2y times dy equals 0, using the chain rule. We may then solve for dy to get dy equals negative x over y. Now, let's discuss why implicit differentiation is necessary. The equation x cubed minus 8xi plus y cubed equals 1 is hard to be explicitly solved for y as a function of x. Indeed, the curve can be broken into 3 pieces, each of which passes the vertical line test. Therefore, the given equation determines implicitly 3 functions of x. Let us call them y equals f sub 1 of x, y equals f sub 2 of x, and y equals f sub 3 of x. We do not have explicit formulas for these 3 functions. However, we will overcome this difficulty using implicit differentiation. Let's take a look at this example. Although we cannot explicitly solve x cubed minus 8xi plus y cubed equals 1 for y in terms of x, we can find the derivative of any one of the 3 functions defined implicitly by the equation shown on screen. We can use this formula to find the slope at any point on the curve. For example, we have found the slope at these 3 points. Now let's move on to another example. Find df over dx for sine of f plus f equals x. To solve this problem, we differentiate both sides of the equation to get cosine of f times dy over dx plus dy over dx equals 1. Solving for dy over dx, we get dy over dx equals 1 over cosine of f plus 1. Next, let's discuss a special application of implicit differentiation, derivative of inverse function. Suppose a differentiable function f has an inverse f inverse. Find the derivative of f inverse. To solve this problem, let y equals f inverse of x. Then, because f and f inverse are inverse functions, f of y equals x. Hence, differentiating implicitly, we have f prime of y times dy over dx equals 1. Now, solving for dy over dx, we get dy over dx equals 1 over f prime of y, or left bracket f inverse of x right bracket prime equals 1 over f prime left parenthesis f inverse of x right parenthesis. Let's take a look at some examples where we can use implicit differentiation to find derivatives of inverse functions. First, find the derivative of y equals natural log of x using implicit differentiation. Presuming that we don't know the derivative of natural log of x, we would rewrite this equation as e to the power y equals x using the inverse function. Now we can use implicit differentiation to find e to the power y times dy over dx equals 1, so dy over dx equals 1 over e to the power y, which is equal to 1 over e to the power natural log of x, which is equal to 1 over x. Next example. Find the derivative of y equals sine inverse of x using implicit differentiation. Rewrite the equation as sine of y equals x, and differentiating we find cosine of y times dy over dx equals 1, so that dy over dx equals 1 over cosine of y, which is equal to 1 over cosine left parenthesis sine inverse right parenthesis left parenthesis x right parenthesis right parenthesis. To simplify, we recall the useful identity sine squared left parenthesis x right parenthesis plus cosine squared left parenthesis x right parenthesis equals 1, which leads to cosine left parenthesis x right parenthesis equals square root left bracket 1 minus left parenthesis sine left parenthesis x right parenthesis squared right bracket. When we substitute into the above equation, we will apply sine to its inverse yielding x and find d over dx sine inverse left parenthesis x right parenthesis equals 1 over cosine left parenthesis sine inverse left parenthesis x right parenthesis, which is equal to 1 over square root left bracket 1 minus left parenthesis sine inverse left parenthesis x right parenthesis squared right bracket, which is equal to 1 over square root left bracket 1 minus x squared right bracket. And that concludes our presentation on the chain rule and implicit differentiation. Thank you for your attention, and I hope you found this presentation informative and engaging. Have a great day.